Thank you very much. Good morning, everybody. This is joint work with Kedar Nam Joshi, who's also in the audience and also at POPL, and Yaniv Sar. It's about synthesizing this special class of programs that we call coordination programs. As the name suggests, a coordination program is a program that coordinates other interesting programs. For example, consider an IoT setup. For instance, we want to look at a temperature monitoring unit in a smart home. It consists of multiple devices, a heater, a cooler, and a sensor. And then the centralized coordinator here would be the thermostat that interacts with each one of these three devices in order to maintain ambient temperature. Another example would include automated industrial warehouse. It consists of multiple specialized robots, and you can imagine a centralized coordinator helping these robots to collaborate in order to carry out a task. Yet another example comes from the area of web servers, where the idea is that there are many web servers and you want to have one centralized server that oversees all of the activity. If we step back a bit and think of these setups in a more abstract manner, we could think of it as consisting of one coordination program and multiple other agents or devices. These agents and devices may or may not interact with each other, and the task of the coordination program is to interact with these devices in order to fulfill some task. And as you may have guessed, designing any kind of a program is hard. In this case, it might be a bit harder because you're trying to coordinate multiple agents, but there are certain features of this setup which make the problem of designing a good coordinator even harder. The first issue is that a coordination program is a reactive system. It does not interact with the agents only once. It interacts with the agents repeatedly over a prolonged period of time. And as these interactions proceed, the state of the coordination program may change because it has to remember the history of interactions. Furthermore, these agents are independent devices, so they may operate on their own clock tick, which means that the system is inherently asynchronous. Furthermore, the coordination program has limited visibility of the actual state space of every device. The coordination program only interacts at an interface, which lets it see some of the activities occurring within the devices and not all of them, which means that there's also partial information in this setup. And despite all of these challenges, we want to design a correct coordination program. While designing something from scratch may seem daunting, a lot of times it is observed that in these cases, it might be easier to specify the intention of a coordination program. For example, in the thermostat case study, one could say that the intention is simply to maintain ambient temperature. So the big question here is it possible to automatically generate a coordination program from a high-level description of a specification? That is what we call the coordination synthesis problem, and that's what this work is about. So in this work, we contribute towards formulating, solving, and demonstrating the utility of coordination synthesis. The idea to synthesize a centralized controller has been explored in prior work, but in those works, all of the specifications are given in a low-level specification language. Given how complicated this setup is, that might be extremely cumbersome. So the focus of our formulation is to be able to capture the intricacies and complexities of a coordination setup and do it in a way which is easy to specify. We solve the problem of coordination synthesis using automata theoretic techniques, but the bigger technical challenge here is to be able to integrate the three challenges I mentioned, to be able to integrate reactivity, partial information, and asynchrony. Most prior work can integrate at most two of these three challenges. Finally, we demonstrate the utility through a couple of case studies and show that coordination synthesis indeed helps in designing good coordination programs. So, for the high-level specification, to describe the intent of the coordination program, we use good old linear temporal logic. It's extremely expressive. It can specify safety, liveness, and many more interesting properties that you could possibly think of. The harder part here is to describe the devices. The devices, imagine the devices are actually really interesting looking things like sensors, heaters, ACs, and so on. So they have a rich structure. Plus, recall that they must have a communication model because each device interacts with other devices as well as interacts with a centralized coordinator. Plus, it must have an interface that demarcates between what are the actions the coordinator can see and what are the actions that are hidden from the coordinator. Describing all of these three features in a low-level specification language like LTL can be extremely cumbersome. So instead, we use this well-established notion of communicating sequential processes, which give all of these things for free. So let's look a little bit more into how do we describe a device in CSP. So a CSP process, first of all, has an interface. So it has a set of public actions which are visible to all other devices and the coordinator program, and a set of private actions which are visible only to itself and no other device and the coordination program cannot see these private actions. These actions help, then a process is defined as a set of equations which describe how does the process evolve. For instance, on a given action I, the process P may evolve to a different process Qi. That's how we take care of the interface, by demarcating public and private actions from each other. As for the rich structure, CSPs allow structural non-determinism, which means that from the same process on a single action, the process may evolve to two or more different states, two or more different processes. So a device is simply a collection of such processes. You can also visualize a device as a finite state machine, where the states refer to processes and transitions between states show how evolutions occur. As for the communication patterns, CSPs can communicate either through synchronized public actions. So given two processes, they will evolve together if they share a public action. For example, here, process P0 and P1 share both evolve on public action A, which means they share a public action. Therefore, the composition of P0 and P1 evolves together on the action A. On the contrary, if I gave you P0 that evolves on A0 and P1 that evolves on A1, the composition in this case will not evolve at all. CSPs can also interact through internal private actions, which means that as long as a process can evolve on some private action, it can do that without changing the state of any other process. For example, here process P0 can evolve on private action B. So in the composition with P1, the state of P1 does not change in this interaction. So just to put things together, two CSPs could be defined as follows, E, and two devices can be defined as follows, E and M. And then when these two things interact, there may be several ways for them. There will be several ways in which these two things can interact. One possible way is in which first E and M interact on the shared public action A0, and then process E evolves to E0 from where it may conduct private actions only, in which the sequence of actions would become A0 followed by B0s only. In another form of interaction, what may happen is that after the interaction with A0, it may evolve to state E1, from where again process M, again from M0 and M1, it may conduct another shared action on A1. So when two devices interact, there are several ways, several sequences of private and public actions could possibly occur. So the problem of coordination synthesis can be formalized as follows. Given a CSP environment E, which in itself is the composition of many other devices, E1 to En, and given an LTL specification S, this specification is defined over both the private and the public actions of the environment E. Can we synthesize a coordinator M, which is also a CSP, such that the composition of E and M for all possible sequences of public and private actions in E and M, all of them satisfy the specification S. And now, as you may have guessed, the coordinator M can only see the public actions. So without being able to see the private actions, it should be able to ensure that the composition of E with E of M satisfies S. So that's the real challenge here. So breaking it down, one reason why coordination synthesis can become difficult is because the coordinator may not know what the current state of the environment is. This may occur due to structural non-determinism or even internal actions, which are basically not visible to the coordinator from the outside. Not knowing what the current state of the environment is could also lead to difficulties in being able to ensure deadlock freedom. When two systems coordinate, we do not want them to deadlock, and a poor choice of a coordinator may or may not result in a deadlock. So it is necessary to guarantee that whatever coordinator we generate, it does not result in deadlocks. And finally, asynchrony is a bigger challenge because from the coordinator's point of view, all it has seen is the sequence of A0, A1, A2, A3, and so on. It only sees the public actions. In reality, the sequence of executions may be interspersed with private internal actions. And it is this sequence which is not visible to the coordinator that the specification needs to be satisfied on. So for every possible sequence that the coordinator sees, each expansion of it should be able to satisfy the spec. Now, without going into much details, the core idea is that we can show coordination synthesis with an environment E and a given specification S can be reduced into the synthesis of a new transform specification. And this transform specification can be synthesized using standard synthesis techniques that are present in the literature. So as long as this reduction is efficient, we have been able to give you a way to synthesize, to conduct coordination synthesis. In the constructions, we use automata theoretic ideas to be able to encode each one of the three challenges I showed. For instance, in this case, when the coordinator sees the sequence of public actions, it should be able to guess and verify that every expansion satisfies the sequence S. And for this we make use of non-determinism in automata theoretic domains. As a result of which, we are able to show that the new transform specification that we generate is only twice the size of the environment E and the size of the automaton for specification S, which means that this reduction is efficient as well. But only theory and no practice is not as much fun. So we've implemented this tool, implemented the whole pipeline in this prototype tool. The front end as you can see, takes as input an LTS specification S and descriptions of environments E1 to En. We use existing tools Spot and FTR to perform initial parsing, which are then passed into the core area where the reduction occurs. It's written in Python and uses BDD library buddy to conduct the underlying operations, which is finally pushed into the backend, for which we use an existing synthesis tool. I'll only go over one case study, and the objective of this case study is to understand how coordination synthesis really helps in designing a good system. So here we look at a thermostat case study. So we're given three devices, a room temperature sensor, a heater, and an AC. The room temperature sensor changes its state based on what the current temperature is. It could change due to the state could change due to alterations in the physical environment temperature itself, or because of the heater or AC switching on or switching off. And the purpose is to synthesize a thermostat which interacts with the sensor to probe what the current temperature of the room is, and with the AC and heater to switch it on or to switch them off. So we start with a simple specification that says maintain ambient temperature. And then we push this through our synthesis tool, and the coordinator we get is one that actually does nothing. What it says is that, well, because there are going to be changes in the physical temperature, there is no need for it to coordinate. Eventually, temperature will come to something ambient. It's almost after saying, if you've come to New Orleans in the winter to see the sun, wait till summer arrives. So that's definitely not the right coordinate. That's definitely not the kind of coordinator we want. So instead, we can go ahead and keep refining the specification. So we don't refine the system itself, we refine the specification. And by series of refining the specification, we can keep doing that until we get a coordinator with which we're satisfied. And this is really how we envision coordination synthesis being used. It lifts the refining step from refining a system to refining a much higher level specification. So in summary, this talk was about coordination synthesis. We formulate and solve the problem. Our formulation is such that we attempt to encode the underlying intricacies of a coordination setup and do it in a way which is easy to specify. We only touched upon the details of how the algorithm works out, but of course there are many interesting details in the paper that you can refer to. And finally, we also do a complexity analysis, so typically synthesis tasks are expected to be double exponential in size of the spec, so that's not surprising. What is interesting here is that it is p-space hard in size of the environment itself. More crucially, it is exponential in the number of devices. So moving ahead, this opens up opportunities to think of solutions which could scale better with the number of devices and possibly use techniques from verification to make these things work out much better. With that, thank you for your time, and I'll be happy to take questions.
So very nice talk. So I have a question about non-determinism actions. So how often do you have non-determinism actions in for the sensors, and does that impose a scalability issue?
So if you, let's go back actually. So okay, this is unfortunate, but so if you remember what this pipeline looks like, the input is just a sequence, is just a set of devices, and then you rely on existing tools to flatten it into a single environment. And when you do that, non-determinism may get introduced into the system by itself. So it is reasonable and it is necessary to have non-determinism in the setting as well. And yes, it does, removing non-determinism make the problem a bit more simpler, but not by too much. At least not complex in terms of complexity theory.
Right. Thanks very much for your talk. I get a bit nervous when I see a coordinator, because it looks like a single point of failure to me. And so I was wondering if your technique could generalize at all to synthesizing systems where every agent does a bit of coordination itself, and so you spread the risk around the system.
So that is a very good point. We do want, so what you said, if it's like a one-stop shop. If the coordinator fails, we don't want the whole system to fail. So one idea behind allowing the agents to have internal actions and to be able to communicate internally with each other is to be able to gracefully get out of these ugly situations. But in principle, it is there. It would be really nice if we have a case study where we can show that as well. But maybe we should talk about the case study. All right, sure. Thank you.
Thank you.